Good afternoon, everyone.
Good afternoon, sir.
Sorry, rain has been affecting me so bad, and I think now I've stabilized. How far have we gone in modern physics? Had we discussed the Albert Einstein's mass-energy relationship? Which included binding energy per nucleon. We looked at examples. How many examples did I give? Did I give an assignment? I think we are going for fission and fusion. But before that, let me just remind you by doing this number. Calculate the binding energy calculate the binding energy per nucleon for iron 56, 26, given that mass of a neutron is equal to 1.008665 U. Mass of a proton is equal to 1.007277 U. Mass of an electron is equal to 0.0 0.0054858 U. And then mass of iron 56 is equal to 55.9349 U. Now, first and foremost, we need to know iron 56, 26, will give us a neutron, which is 1, 0. It will give us protons, which are 1, 1, plus electrons, whereby you discover that according to this, we shall have, if I balance the equation, I will have, if I have this as 30, first of all, because of the mass number being 26, it means that the number of protons have a high likelihood of being what? 26. The protons are 26, you'll have atomic number 26 plus 0 you'll get 26. But now there's a challenge of electrons. Okay, there's a challenge of electrons. Then we would have how many electrons? Remember, the number of protons are equal to the number of electrons. And then how many protons shall we expect? We shall expect to have 30 neutrons, whereby 30 times 1 plus 26 will give us 56, plus the 0 on the electrons. But number of protons is equal to number of what? Is equal to number of electrons. So therefore, from that knowledge of electronics, of atomic structure, we can have the mass of the neutrons as being what? 30 times the mass, which is 1.00866 U. Compute and give me the answer. Then we shall also have mass of the protons, which are going to be 26 times 1.007277 U. We shall also get the answer. And then lastly, we shall have mass of the electrons, whose number is the same as that one for protons, which is also going to be 26 times 0.000054858 U. So what is the first answer? Calculate, what is the answer? 30 times 1.00866 U.
It's 30.2. 30.25995.
Then the second one.
$26.1892.
One.
It's 26.189202.
188.
26.189.
Then for the electrons. What do we have?
0.1.
1.42.
0.01426.308.
Like that? Then you get the total mass of the nucleons and electrons. So sum up all those answers we have got.
308.
It is what? $30.25915 U plus 26.8920 2U plus 0.0142208 U. When you sum this up, what do you get?
56.
56 points.
4634.
463
4.
U. Now we need to get the mass defect. The mass defect is equal to mass of the nucleons plus electrons minus mass of the atom. And this is going to be 56.4634 minus 55.9349 What answer do we get? I forgot I should have given you one U as 1931 mega electron volts.
Zero 0.5285.
0 point
5.
So now binding energy can be got from 0.52852 times 931 mega electron volts. What answer do we get? 400 something, 400.
492.
400?
92.
Mm.
0.0335.
Mega electron volts. Now, if they asked for binding energy per nucleon, it is binding energy over the mass number. So it's going to be 492.0335 divided by the mass number, which is 56. What answer do we get? Sente zipo. Airtime. Answer? Back off. Guys, no one has pressed the calculator. Yeah, when you get
Teacher, 8.78.
8 point. 8 point.
7863.
8.7863 mega electron volts. Now remember, if they tell you to leave your answer in mega electron volts, you stop there. If they say find your answer in joules, you must convert and say this is 8.7863 times 10 to the power 6, the million, times 1 electron volt, which is 1.6 times 10 to the power negative 19. Here, the answer now, you'll get it in joules. Can we try to get that answer in joules?
One point 1.4058 exponent negative 12. Teacher, we cannot hear you.
Yes, I was saying, if they ask you for just energy, then you go and get energy in terms of its SI units, which are joules. So you convert up to joules. If they ask you for energy in mega electron volts, then get the answer in mega electron volts. So you'd have stopped here if it was asking for mega electron volts. So have that down, then we have another number before we can introduce something new for today. Okay, hope we are done. Let's have another number. I think I sent this number. A nucleus of uranium. A nucleus of uranium 238 disintegrated. Disintegrated with emission. With emission of a nucleus X and an alpha particle. write down the equation for the reaction. Today's rain is joking. We shall study. This rain is joking. Sorry, the rain is, I think, interfering with the network, but it shall be fine. So let me write it again. I was saying a nucleus of uranium (238) disintegrates with emission of a nucleus X and an alpha particle. Question 1, write down the equation for the reaction. Equation 2, find the energy released in the reaction in mega electron volts. Mass of uranium 238 is equal to 238.1249 U. Mass of X is equal to 234.11650 U. Mass of helium is going to be equal to 4.00387 U. 1 U is equal to 1.667 times 10 to the power negative 27 kilograms. Remember, I told you when they give you 1 U in kilograms, you use the Albert Einstein's mass energy relationship. When they give you 1 U in mega electron volts or in joules, you just multiply by the mass defect and get the answer. So the equation would be uranium 238 92 disintegrates to a nucleus X plus an alpha particle, which is a helium nucleus of mass number 4, atomic number 2. Because this is a 2, this will have an atomic number of 90. This is 238. When you take off the 4, this will have 234. And hence, that is our balanced what? Equation. It's just that we knew the alpha particle, it's always a helium nucleus of mass number 4. Then the X, whose mass number and atomic number we didn't know, we could now deduce it from that by subtracting from the mother nucleus of uranium. Now, with that, we can get the mass defect. The mass defect is going to be mass of uranium. If you get, for example, this one, you will see that when you sum the two, mass of uranium is what? Mass of uranium is 238.1249 U minus, I think I need to write down something. Mass defect is equal to mass of uranium minus mass of X, which is 234, and the alpha particle. Now, when do I know that the mass of uranium is the one that is subtracting the mass of the nucleons which we have got? It's because when you look at this value, 238, this value 238 is greater than the mass number we know. But if it is less, for example, if they had given you 237 point blah, 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 U, it means the mass of the nucleons is the one which is greater than the mass of the atom. But now if the mass given here is greater than the mass of the atom, then you use the mass of the atom minus the mass of the nucleons. So for that reason, I will say 238.12492 U minus mass of X is what? 234.1165 U plus mass of helium, which is the 4.00387 U, close brackets. When you press the calculator, what answer do we get? But remember, these numbers, you have to be patient with the digits. Eh? If you rush them, you'll crash and have wrong values.
$4.55.
0 point. Okay, you said 4 point.
4.55
times 10 to the power
exponent -3
U. That is our mass defect. Now, the other new challenge, or the other idea I need to remind you is that if they give you in terms of kilograms, we need to get the mass defect from the change in mass times C squared, which is Albert Einstein's mass energy relationship. So this is our binding energy, which is the change in energy. So for that reason, the binding energy will be equal to the mass defect, which is 4.55 times 10 power -3 times 1.6 times 10.66 times 10 power -27. Now this is the mass in kilograms times the speed of light, which is 3 times 10 to the power 8. But the whole of this is squared. When you press your calculator, get me the binding energy.
$6.798
6.798 times 10 to the power
times 10 -13.
Now this one takes you straight away to joules. Eh? Now they said, find the binding energy released in mega electron volts. So because this one has brought us to joules, they want us to convert to mega electron what? Volts. Now, if you recall, 1 mega electron volt is equal to 1 times 10 to the power 6 for the mega times 1.6 times 10 to the power negative 19 joules. That means 1 joule is equal to 1 mega electron volt divided by 1.6 times 10 to the power negative 13. So for that reason, the 6.798 times 10 to the power negative 13 joules will be equivalent to, they're going to be equivalent to 1 over 1.6 times 10 to the power negative 13 times 6.798 times 10 to the power negative 13 mega electron volts. I can lose the exponent 13 with this one. When you press the calculator, what answer do we have?
$4.249.
Mega electron volts. So we have reactivated ourselves very well with the binding energy and mass defect. Now, with that, unless if someone has a question, I would like us to advance and go to nuclear fusion and fission. When we finish this concept, I will introduce X-rays. Yeah, do we have Google? Do you all know how to access Google Classroom? I wanted to give you a test. You all know. Okay, so with that, we can introduce what we call nuclear fusion. Just like you've heard of the word diffuse, the word diffuse means you're putting together items. You're fusing your two fingers into each other. Even here in nuclear energy or in nuclear fusion, we have what we call fission and fusion, whereby fusion talks about the merging of nucleons together, while fission will talk about splitting them from each other. And with that knowledge, we shall see how this all can be handled when we have fusion and fission. There's something I wanted to share with you here briefly in nuclear physics. I'm still opening my book so that you can see it. Let me give you some insight of nuclear energy here. Sorry, there's something I want to share with you. Okay, hope you can see that screen for that book. Though our country's syllabus is still very, I don't know, very backward, they are building a new one. Perhaps your young ones who are in senior 1, because the senior ones have already kicked off with the new syllabus, by the time they reach senior 6, they will be also studying this same course, other than you guys. So here, when you look at this, it talks about the types of decay, which we have all, those ones are the same as what we know. This is basically what is taught by whites, USA and UK. And this is what they call the GSEU course. Now, for them, they go beyond the atom. They go beyond the electrons. They go beyond the protons and the neutrons. I don't want you to go to UK or to the US and you go to MIT or to Harvard or Oxford and they talk about these things and you say, our teachers never knew any of this kind of physics. I just want to give you an inspiration of this and you get to know how some of these things come about. Now, according to nuclear physics, which is latest, just like you've heard that there is another state of matter, which is called the plasma state of matter. Here, we don't teach it in Uganda, but I think the new syllabus has now included it. Yeah? Other than having gases, solids, liquids, we also have plasma. Now here, also I want to show you that beyond the electrons, beyond the protons, beyond the neutrons, we have what we call quarks. And the quarks are the fundamental particles we have, just like we have the fundamental quantities. Whereby a fundamental particle is that particle that cannot be split into anything smaller. But as we speak now, electrons are fundamental particles, but protons are not, and even nucleons are not. Meaning electrons cannot be split any further, but we can split protons, we can split neutrons. When you're splitting them, we are carrying out what we call nuclear fission. When we are merging them, we are carrying out what we call nuclear fusion. That is why I brought it in this area. So protons and neutrons are made up of different combinations of smaller particles, which particles are called quarks. And the quarks are these ones right here. These are our quarks here. So a table of quarks, we have what we call an upward quark, and we have a downward quark, whereby an upward quark has a symbol U, a downward quark has a symbol D, and they have charges of positive 2/3 and negative 1/3. And then we have what we call a strange quark, which is represented by S, and also it has a charge which is negative 1/3. Now, why I want to bring you this knowledge, because I want to show you how do we come up with a neutron and a proton to be having mass numbers 1. This is where my knowledge is today. I want to show you this. That if you merge an upward quark, yeah, and you merge it with another upward quark, eh? This is upward, this is also upward, and then you merge it with a downward quark. So two upward quarks and one downward quark, when you sum them up, remember we have said an upward quark has plus 2/3. So you get plus 2/3 plus 2/3. When you add them, and then you add on one downward quark, a downward quark has a negative 1/3. You will get 4/3 minus 1/3, which will give you a positive 1. A positive 1 induces what we call a charge, which we have for a proton or a neutron. Now, this is for proton. That is why the proton has mass number 1 and atomic number 1. So it has one electronic charge. That is where its 1 came from. Then when you go to a neutron has one upward quark, which is this one U. Then it has 2 downward quarks. So the 2 downward quarks correspond to negative 1/3 plus negative 1/3, which gives us a negative 2/3, plus 1 upward quark, which is 2/3. The answer is 0. That is why a neutron has 1 mass number and 0 atomic numbers. And that is why the neutron has no charge. Have you appreciated the physics I've shared today? That is the physics, which is the latest nuclear physics of the fundamental origin of elements or particles we have in the world. But our physics in our country has not yet come to that. We are still very far away behind this. Even universities don't teach this. But I wanted to show you so that you appreciate. That is why I say when I ask you to visit the internet, go visit the internet and read some of these things. Then the other ones, I will not go into details of the antiparticles, of the antiquarks, downward. Those ones, let me not go there. Let me just stop here. And then now we can go back to our splitting and fusing of nuclear particles. That is nucleons and protons, perhaps. Okay, so with that knowledge, we now know where the neutrons come from and the protons, and we now understand that they can be merged together. This fusion is for merging, Fu. Then Fi is for splitting. Eh? So therefore, this is the combination of 2 light nuclei. Now what happens is, these nuclei are looking for stability in most cases. When we have unstable nuclei and we merge them together to gain stability, then we shall say we are carrying out what we call nuclear fission. So by definition, this is the combination of 2 light nuclei to produce a heavier nucleus, which is going to be accompanied with the release of what? Accompanied with the release of energy. An example of, I will send the notes. An example of fusion is the combination of 2 deuterium nuclei. Deuterium is written like this. Deuterium. An example is the fusion of 2 deuterium nuclei. Nuclei is the plural of nucleus, whereby deuterium is H21 plus H21. When you fuse these 2, you'll get helium. Helium-3. Helium is He over 3 over 2 plus 1 neutron plus a release of energy. So when you merge 2 deuterium nuclei, you'll end up achieving what we call a helium of mass number 3 plus a neutron, and you'll have it accompanied with a release of what? Of energy. So with that, you have fused 2 nuclei of deuterium to produce a helium nucleus, which is having a mass number 3, and a neutron with a release of energy. So the energy you release in this case is what we call the nuclear energy of fusion. Reactions of this type are the source of the sun's energy. So some of the uses of fusion, they can ask you relevances of fusion. We get sun's energy as a result of fusion of hydrogen what? Nuclides. The fusion to occur must have very high kinetic energy. So you cannot carry out this fusion if you don't have enough energy given to the nuclei. So the nuclei must be subjected to a very high kinetic energy, as it has to overcome the electrostatic forces of repulsion forces. We have given an example of hydrogen in the sun, fusing the hydrogen what? Nuclei in the sun. These nuclei, remember, they are the same. They have the same charges, they have the same mass number, they have the same everything. So when you bring them together, they will experience a repulsion force. Now, when you when they experience a repulsion force, they will require to have a lot of kinetic energy for them to come together so that they can beat or they can overcome that repulsion force between them. So for that reason, you need a very high energy in order to overcome the electrostatic force of repulsion forces between the two nuclei. This high kinetic energy is attainable at very high temperatures. So meaning you need a very high temperature. That is why the sun is very hot. So the sun can facilitate such kind of reaction because it has a very high temperature and gives these nuclei high kinetic energy so that they are able to overcome those electrostatic repulsion forces. Hence, this confirms that a very high temperature is always needed when you're carrying out fusion. That is what happens when you're looking at nuclear fusion. Then for nuclear fission, the difference I've told you is this one merges nuclei, then the other one is nuclear fission. This one splits. Splits what? Splits the nucleus into other fragments or into other nuclei. So this is the splitting or disintegration of a heavy unstable nucleus into lighter or into fragments or into lighter stable nuclei of roughly equal masses with the release of what? With the release of energy. Just like all of us have ever split a cake. You get a cake and break it into two. Yeah? In that case, you are fizzing the cake. When you get the two pieces and bring them together, you are fusing them back together. Right? So with that reason, you would be carrying out what we call nuclear fission. And with this, energy is released in the process because the average binding energy per nucleon of the fission products is always greater than that of the parent. So in this case, the energy of the parent nucleus is always smaller than the energy of the daughter nuclei that are coming off this nucleus. Now, one example we can talk about here is when uranium has been bombarded with a neutron. Yeah? Two roughly equal fragments are produced with the release of energy. Now, sometimes they might want to split a nucleus, but they bombard it with other particles. Maybe you want to split anything, maybe cobalt, you want to split uranium, you want to split whatever. Then you bombard it with neutrons, or you bombard it with alpha particles, or you bombard it with protons. Then they can induce very many fragments, very many particles, very many nuclei can come out of them. So one example we can always talk about, which is a very common example, is the bombardment of uranium-235 with a neutron. When we bombard a uranium-235, 92, and we bombard it with a neutron, then it is going to produce these fragments. One, we shall produce uranium-236, 92. But this uranium-236, 92 can be split into one, barium-141, 56. We can also induce krypton. Krypton, 92, 36. We can also induce 3 other neutrons plus a release of energy. This is nuclear fusion of uranium. Uranium can be bombarded with a neutron to form uranium-236-92. Then afterwards, this uranium-236-92 can be disintegrated, yeah, into barium, krypton, and 3 other neutrons as the particles which are being released, plus a release of energy. But these particles which are released, they have a bigger energy than the mother nucleus. Now, in this remaining time, there is a derivation which they normally ask for, or they can ask you about. They can ask you for the kinetic energy of the daughter nucleus on splitting, after splitting. If you have a mother nucleus, and this mother nucleus splits into a daughter nucleus, yeah, plus maybe an alpha particle, then this will be mass of the mother nucleus, and this will be mass of the daughter nucleus. We shall also have here mass of the alpha particle. Now, because this mother nucleus initially was not moving, it has an initial velocity 0. Then we have here velocity of the daughter nucleus. Then here you have velocity of the alpha particle. But remember, when these items are splitting, they split. When a particle is splitting, they don't split going in the same direction. No. This one can split going this way. This one can split taking this direction. So this one can be given a negative, or the other one can be given a negative. So with that reason, if one of them is given a negative, then from momentum conservation, total momentum before is 0 because they are not initially moving. Momentum after will be mass of the daughter nucleus times the velocity of the daughter nucleus plus a negative of mass of the alpha particle times the velocity of the alpha particle. With this reason, we can see that the mass of the daughter nucleus times its velocity is equal to mass of the alpha particle produced times the velocity of the alpha particle. Now, because energy is a constant, we have energy conservation. Remember, we said we need very high kinetic energy. We need very high energy for this to take place. So we shall expect total energy before to be equal to the energy of the daughter nucleus plus the energy of the alpha particle by energy conservation. And in this case, this is the total energy released as a result of these two coming out as splits from the mother nucleus. But this energy is kinetic. So the total energy, if it's capital E, it will give us a half m of the daughter, v for the daughter squared, plus a half m of the alpha times v for the alpha squared. If they ask you for energy of the daughter nucleus, or if they ask you for the speed of the daughter nucleus, then we can say from this equation 1, I can make the velocity of the daughter nucleus the subject, and I'll have mass of the alpha particle, velocity of the alpha over mass of the daughter nucleus. So the total energy would become a half times mass of the daughter nucleus times mass of the alpha, velocity of the alpha over mass of the daughter, but the whole of this is squared, plus a half of mass of the alpha, velocity of the alpha squared. With this, you can factorize out the velocity of the alpha particle squared. And when you look at this mass of the daughter nucleus can die with one mass and remain with one mass here. So for that reason, when I simplify the bracket, I'll have, this is over 2. I'll have mass of the alpha squared, velocity of the alpha squared. Okay, factorize out the velocity of the alpha over mass of the daughter nucleus plus mass of the alpha nucleus, close brackets. I have factorized out V alpha squared on the second part. Even here it went out. Therefore, I can take out mass of the alpha particle, which will give me mass of the alpha particle, velocity of the alpha particle squared divided by 2 into brackets, mass of the alpha particle over mass of the daughter nucleus plus 1. All this is equal to total what? Energy. Now, when you look at this carefully, you see that you have a half mass of the alpha, velocity of the alpha squared. It can be expressed in terms of the energy times mass of the daughter nucleus out of mass of the alpha particle plus mass of the daughter nucleus. This becomes the kinetic energy with which the alpha particle splits. So this becomes the kinetic energy with which the alpha particle is going to explode away. But if they ask you for the speed with which it runs, you look for V alpha by saying V alpha is going to be equal to total energy, which is now twice of total energy of mass of the daughter out of mass of the alpha into mass of the alpha plus mass of the daughter, close brackets, but the whole of this, you put it to power a half. With this, you would have confirmed the energy for the alpha particle on splitting, that is when nuclear fission is taking place. You would have confirmed the velocity with which this alpha particle is going to run away. We have 3 minutes. I want to leave an assignment for you to go and derive for me in your notes. You will derive velocity of the daughter nucleus and also derive the energy of the daughter nucleus. Of course, what you do now, instead of making VD the subject, this time round you'll make V alpha the what? The subject. And then you substitute and you do the algebra. So I expect you to derive something like this. You're going to derive energy of the daughter nucleus as equal to energy, which is total, times mass of the alpha particle over mass of the alpha particle plus mass of the daughter nucleus. Then I'll also expect you to get the velocity of the daughter nucleus as twice energy of the mother of the mass of the alpha particle out of mass of the daughter nucleus into mass of the alpha particle plus mass of the daughter nucleus. But you raise the whole of this to the power a half. So you try those items in your free time. Those are very sensitive parts. They can ask about them. If they don't ask about them, they can ask you. But if you know the equation, you just substitute. If the question comes with over 5 marks, you have to derive. And then you substitute, and then you get the answer. If the question is just 3 marks, you just need to only substitute and get the answer. So next time we shall do some numbers related with nuclear fission and fission reactions. Then also we shall explain fusion and fission using the binding energy per nucleon graph, and which is against mass number. But when I'm sending the notes, I'm going to send all of them so that you can take a look at them. So please go ahead and derive those items I've left, unless if someone has a question they wish to pose for me. If no questions, I'm sending the work right away. Okay. who is coming now. Soul weapons. You better tell him it's so early for the next lecture. But let us admit him anyway. Oh, perhaps maybe they are going for thing. It's coming for economics. For what? Submath.
Oh,
Hmm?
excuse me.
Hmm. I will send you the other book and you read about it. I'm going to send you the other book for GSE so that you read some more physics from there. Maybe it can help some of you to understand some concepts. Eh?
Get the note.
What? Yeah?
Oh, that's about what?
What? I can't get you, man.
Where are you going to send the note? Send the notes.
Hey,
Are you going to class?
notes I'm sending them on WhatsApp.
Your WhatsApp number.
It's here. 7828555674. WhatsApp, may I add you to the group?
Okay.
Okay, we have a good evening.